Hey, this is Josh. In this video, I'll be going over my personal overview of the Lecture 2 of the Plutus Pioneer program. Reading the title of this video, you'll know that this video will be all about validator scripts and how to implement it. So we'll be going over the 6 examples that went through in the official lecture video, and then we'll also be going over the 2 homework assignments that was assigned to us for this week. Warning ahead, this video will be highly technical in nature. I do my best to try and make the Haskell code understandable for those who have understanding of computer programming. However, that is no substitute for an actual knowledge. Now, do read the links below in the description. It does include commands and other helpful links that might help you get you started. Otherwise, this video is going to be quite long, so let's just get started. All right, so we're back inside our Ubuntu VirtualBox. So a quick recap of what we did in the previous video. For people like me who had a Windows machine, I set up a Ubuntu server with VirtualBox, which allows us to run our own instance of the Plutus playground. Now we take a quick look inside. I made a folder called Plutus, which we store all of our repository. And inside of that, we have 2 repos that we cloned, Plutus and the Plutus Pioneer program. Now, for those of you who want to follow along in the lecture 2, but don't have the Plutus Pioneer program repo, you can just do git clone and put the URL to the repo, which I've included in the description below. And so we go inside Plutus Pioneer program, go inside code, and you'll see that there's 2 folders, week 1 and week 2. For those of you who was an A+ student from last week and cloned their repo, you might only see week 1. So if you want to get the latest bits, just make sure you run git pull to get everything. Now we just go to 2, go inside source, go inside week 2 again, and we'll see there are 7 files here. Homework 1, homework 2 is our homework for this week, and the other 5 files is the examples that I went through in the lecture. Now, if you wanted to follow along and actually build the code or run your own instance of the code, you could run cabal REPL, but you might run into some problems. So instead of going through the arduous process of installing it, there's an easier way. We can just use the cabal that's inside the nix-shell environment. So we just go all the way back, enter our Plutus repository, run nix-shell, and this would set up an environment that would have all the tools that we need. So I'll just let this run and we'll resume when this finishes. All right, so now that our nix-shell is finished, we'll just go back to directory, go inside our Plutus Pioneer program, go inside code, and then week 2, and then we'll just run our cabal REPL. This will take some time to build and compile everything. And here we are. So we can play with this and we can do something like import Plutus TX. There. Oh, yes, Plutus TX. And you get to play around with the Haskell code just like what was done in the lecture 2 video. So I actually want to go through the examples on a great free website called playground.plutus-community.com. Unfortunately, at the current making of this video, that website's down. So it looks like I'm going to have to just create my own server again on my local environment. If we recall how to do that, we need to exit a cabal, which you can do with Control-Z. And we have our first nix-shell. And so for those who don't remember, we go into back to our Plutus repository. We go inside Plutus Playground Client, and then we just run Plutus Playground Server. Now we need to set up another terminal tab, run nix-shell again, and then this will be our local client that we connect to. So I'll just let all of this run for now. All right, we have our second nix-shell, so we just go back, go inside the Plutus Pioneer program. Oh, sorry. We're back at Plutus, and all we need to do is go back into the Plutus Playground client and just run npm run start. And then this will run the local client that will connect to our server on this other terminal right here. Let's just let this run. All right, so now that our npm run start finished, we go up, we take the location of the URL, just copy it, open Firefox, and just go visit our local instance. And there we go, we have our own instance of the Plutus playground. Let's make it 200%. So first things first, let's go through the 6 examples that was walked through in the second lecture. So the first example that the lecturer went through was the get Haskell file. Copy everything in here, open up our VirtualBox again, and then just paste. So the big focus of week 2 is a concept called a validator script, which is what we see right here. So in Plutus, there's a concept of on-chain and there's a concept of off-chain. The validator script that we're writing is a on-chain. Specifically, what on-chain means is it's the code that's actually running on the Cardano blockchain itself. And then we have the off-chain, which is the code that runs on your wallet. This is the code that sends transactions from your wallet to the script. So for those of you who are unfamiliar with Haskell, this might look very confusing. But the crux of it is the MK validator is essentially a function. And to read this, this is the declaration of our function. We have 4 variables. 3 of them are data. I'll talk a bit more about them later. And the last one is always the return type. This 2 parentheses is called a unit, or you can basically think of it as void. What this function is, if you were to translate to something like Java, is we will return, it would be a function called public void, and we would call this MK validator. And this MK validator would take in 3 parameters: data, an object of type data, a variable B of type data, and finally a variable C of type data. And then you just write your code. Write code. Now, the lecturer also went into what this data object is. Essentially, data you can think of is a separate class that has multiple constructors. Continuing off our Java example, we can have a public class data. And then we have multiple constructors that we can define our data. I'm just pulling public data list, which also contains data. And this is one possible constructor. Another one could be public data. We're given a I value, and we just call it I, for example. And this is list. And that's what all data is. Data is just a generic type, so to think, that Plutus wrote to allow us to transfer data for our validator script. So great. Now we understand what data is and what essentially make validator is, but we still don't really know what these 3 data that we're actually receiving are, or what the line below it is. These 3 data objects represent user inputs that will be sent over. So the first one is something that was talked about in the previous video and a bit in this video called datum. A datum is an arbitrary data that usually the starter of a script sends. And it can be used to provide extra information for your validated script, or it could be something that can be used to check with your second input, which is called a redeemer. And a redeemer is also another arbitrary data that another user, a wallet, sends. And this is used to make sure that that user can unlock the funds or not if our validator script returns true. And we'll also talk about this a bit later. And then finally, we have something called our context. And this is just information about the transaction. This can be our input and our output. So every Plutus script needs a validator script. And the way to read this second line is that we have make validator, and for Haskell, to be able to use the variables that were passed in, we need to actually call them something. So we need to call them A, B, and C. A will represent our datum, B will represent our redeemer, and C will represent our context. And this next part is our implementation of a validator script. So the most basic example, which is what this code is we would just have a validator script that doesn't do anything, and we just return a unit. What's interesting about Haskell is it doesn't have something called side effects, which is common in object-oriented programming. A side effect, for example, is a function that would change the state of the code. So let's say, for example, we have public class data. We have a field, let's say int, and we'll call it data or something. Doesn't really matter. And let's say we have a function called public void set. It takes in an integer. And then we just say this.data equals A. This function changes the object data. So now it's no longer guaranteed. In Haskell, everything is a pure function, meaning that things like us changing the state of our class is impossible. An example of a pure function is, let's say we have public int get num, and let's say it takes another integer, A, and all it does is it returns A. And this is a pure function because every time you give the function or method a variable, it will always give you the same result no matter what. And so that's what a pure function is. And Haskell is entirely made up of pure functions. So one interesting exception, though, of this make validator script is that we have a function that we pass in data that essentially does nothing. And we'll see this in a later example. But if this function succeeds, we can assume that the validator released the funds, which is exactly what this script does. However, what we could also do is we can, for example, throw an error if the conditions are not met, and then the Plutus script would not release the funds to the user. And that's basically the crux of what a validator script is. It just takes in data from the users and it tries to figure out if you should release the funds or not. Now, to get this code to work for the on-chain part of your code, specifically on the blockchain, we need to compile the code into something called Plutus core. And to do that, we have this very ugly and confusing and scary looking line of code. This is the validator function, which returns a type called validator, which is required to run our code. I won't go too much into detail, but this uses something called Template Haskell. What all Template Haskell is essentially code that generates code during compile time, and then it compiles that afterwards. Luckily for us, we don't actually have to know what we're doing here. It was even said in the video itself that this can just be copy and paste. It will always be the same pattern over and over. So all we need to do every single time is we need to find some function that returns a type validator. We call this function that Plutus provides us called make validator script. And then we just copy this template Haskell code and we give it the validator script that we wrote, which is up here. One thing that I'll bring up now is that the code inside our template Haskell has to be inlineable, as in it has to be written directly in here. And that's a problem if you have very large functions or functions that require other functions. And so to get around that, we have something called a pragma, which is just code or kind of like comments that you put on top of your normal functions or code, and then the compiler will do something fancy with it. What this pragma does is it basically tells the compiler that this function can be inlined, and that's what its purpose is for, so that you can actually put it inside our template Haskell. We now have a function that returns validator. The next step that we need to do is we need to generate the address to our script. And this is important because when we are sending transactions from our wallet, we need to also send information to the script itself so that it can store the information from our validator script. And to do that and get the address, we first need to create the hash of our validator script that we created. And so this function is basically a function called valHash that returns a type validator hash once it's called. And the implementation of this is we call something that Plutus gives us called a validator hash. We call the validator function, which then returns a validator object. So now that we have a function that would generate the hash of our script, we make a new function called source address, which returns the type ledger.address when it's called. And inside its implementation, we call another function that was provided for us called script address, which would generate an address based off of the hash that we give it. And that's all we need to do for the validator script in the on-chain part. Now, I won't dive into the actual wallet code because that will probably be week 3 or maybe 4, but I will scroll down and take a look at some of the wallet code. Now, for those of you who followed along in our Plutus Playground videos, you might actually be familiar with what we're seeing over here. But we, inside our type or object, gift schema, we define 2 endpoints, give and grab, these are actually the actions that you can take in the simulator, and this is how you define them. So the give endpoint would take in a integer from the user, and the grab endpoint would take nothing. Now, if we scroll down a bit, we see a function grab and give. These are basically what the code executes when the user selects that endpoint as an action. If you look inside our code, we see give, and part of the implementation is we create a transaction, and it uses the val hash function that we defined up here. As you see, it's highlighted. And we also create a datum, which we don't need to know what it does, but this is the datum that we provide up here inside our validator script. And so that's our give. And then we look inside our grab example. Grab is also very similar. We use the function source address to get all the UTXO at our script. And then we also, somewhere further down, we create the redeemer type that we will later send our transaction to our code to figure out if this specific user will redeem the ADA or not. Now, let's quickly remove all this code again. And I will hit compile. Compile successful, go to simulate, and I won't run the example, but you see inside our function we have these two actions, give and grab. If we look at grab, or give takes in that one integer that we talked about, and then if we look at grab, it's basically an action that does nothing, which is also what we define in our endpoint. And so that's basically an introduction to validator scripts inside the first example that we went through. All right, so the second and third example that was went through in the lecture was actually combined, and we can look at it in the burn.haskell file. So just like before, we'll just take everything, we'll just go back to our Plutus playground and just paste it. So in here, everything is more or less the same from our previous code. The only difference now is that there's a function called trace error, and it's called no way. What this code does is that whenever you call the validator script, it will just print out an error with the text no way. One thing to point out is that to get this string to work, this is actually a Plutus.prelude string, not a regular string defined by Haskell. To get around this, the Plutus team had to create this new pragma called no implicit preludes and overloaded strings, which allows us to, by default, not load the prelude module every single time the code starts. We had to explicitly import whatever functions or variables that we want to use. And of course, inside our Plutus.prelude, we import everything, including the string. And there's a reason why this file is called burn, because if you look inside our blockchain action, we still have the same two endpoints, give and grab. For give, we lock up 5 ADA, and for grab, we don't provide anything. However, if we look inside the code, inside our validator script, every single time we try to redeem it, we'll throw an error text with the words no way. What this does is it prevents anyone from ever redeeming the ADA back, which means you're basically just burning your ADA that you're locking up. So that's not good. In the next example, we're going to actually implement logic that will help us actually redeem the ADA based off of some user input. So the fourth example is a file called 42.hs. Once again, we'll just copy it, go back into our Plutus playground. We'll see that our validator script has been changed. Specifically, we now actually pass in a redeemer type, which is defined now by R. And with this code here, there's these little parallel lines, is something we call a guard in Haskell. But for those of you who are not used to that, this is essentially, you can think of it as an if statement. So you can say if R equals I42, return the unit, else throw error. Like we talked about in the first example, data is you can think of it as a generic object. It's a object that basically has a constructor for any variable types that you want in Haskell. What this code is doing, it's saying is R, the redeemer type I have, is equal to the integer 42. And I here represents the integer type, which was defined inside the data object. If you looked at the lecture 2 video where Professor Lars looked at the implementation of data, and that's why we can compare R of I, because they're essentially the same type. And so if our redeemer value is 42, then we just return nothing and we're good. However, if R is not 42, we'll throw an error saying wrong redeemer. And so now this fixes the problem from example 2/3, where the money is locked up forever. But if we quickly look at the wallet code, or specifically our grab endpoint, before this was a unit, and now we changed it to an integer because now we want to actually allow the wallet who's calling grab to guess the number. If you look inside our grab implementation, you'll see that now it has a type integer. This R right here represents the name of the variable that we're taking in, which is our integer. We're doing exactly the same thing for everything. The only difference now is that we are passing the R type as a redeemer. To read what's happening over here, we're calling the must spend script output function, which would create a transaction, and it takes in an OREF, and then you see these dollar signs. What are these dollar signs? The dollar signs basically means evaluate the next expression first. So essentially what we're saying is cast our integer that we put in into a type I, which is what our data expects, and then take that value, create a redeemer object, and give that value to the next thing. And so I won't go through the example again. And this is how we start sending custom data to our validator script. But we don't always want to send data. And so in the next couple examples, we're going to look at actually defining and setting more restrictions in these variables in our validator script. So in example 5, we're going to define a different type for our validator script. And so we go inside the type.haskell file, copy, go back inside VirtualBox and paste. So we scroll back to the top and we look in our validator script again. Before we had these data objects that represented our datum redeemer in our context. However, now what we did in this example was that we actually changed them to be an explicit type. And so we never actually used our datum. We just set it to be a unit. The object that we were using was an integer. So let's just call it an integer. And then there's this object that Plutus has called validator context that basically represents all the information you need regarding inputs and outputs and the transaction information. And finally, this function now returns bool. We return true, the transaction succeeds, and we redeem the money. And if it returns false, the transaction fails and no ADA is unlocked. And so if we look at the implementation of the code itself, we still have the same logic. If R equals 42, notice that we're not casting out 42 to an I object anymore. We're just doing a strict integer comparison. If this is true, we just return true. Otherwise, we just return false. To be able to make this whole entire validator script work, we need to define the custom types. By default, the types are all assumed to be data. So if we want to be more specific, we need to set up a type object that will later send to our Template Haskell to tell it what data types we should expect. And so this is just like the Template Haskell, is basically just copy and paste. We create a typed object that has an instance of script type and the typed object where we define our two types, which is our datum and our redeemer. Essentially just copy and paste. And so for these two types, our datum, we would define it to be the unit type. We don't pass anything. And then for a redeemer, we set it to be an integer. And so now we have an object that tells us what our datum and redeemer type is. We need to change our script instance. And this is also a copy and paste. We make a function called instance, or you can call it anything. It returns a script instance object of type typed, which is this whole thing. And so for the actual implementation detail, we use that same validator script that generates the script instance, and then we give it the type the validator script expects. And that's what this @ symbol symbolizes. It tells the compiler that this is a data type and not a specific variable or something. We do the same thing. We use Template Haskell to create our validator. We create this wrap function, which we implement down here. And all we need to do is call scripts.wrapValidator and just give it our datum types and our redeemer type. Everything else stays the same. We just update our code with our new instance. And that's it for restricting the types that we need to send for our validator script. And now we're on to our final example, example 6, where we define a custom type for our validator script. Now, if we look back at our validator script, we now have a custom type called mySillyRedeemer. And if we look at what mySillyRedeemer is, we can see that it's a new type, which basically means I'm creating a new object that is the equivalent of another object, but you're going to call it whatever I define it to be. Specifically, I'm creating a new object called mySillyRedeemer, which acts exactly like an integer. And we do something called deriving, which you can think of as inheritance. We're deriving something called show, which allows us to print things out on the Haskell compiler if we wanted to. We have this line down here called Plutus tx dot is unstable make is data, and then we give it mySillyRedeemer. What this does is you can think this as boilerplate code that executes in the background for you. It's basically saying make mySillyRedeemer a object of type data. Data, as you recall, being this very generic object that represents everything that our validator script expects. And so by doing this, we're allowing our validator script to understand what mySillyRedeemer is. If we look inside our validator script again, we'll see that we retrieve the variable by calling mySillyRedeemer and then r. And one optimization that was done in this code is there's a helpful function that Plutus provides called trace if false. And trace if false takes in two parameter types. It takes in a string and a Boolean. And so if the Boolean evaluation is false, we would print out this message. Otherwise, we don't do anything and the transaction succeeds. Now that we have this custom redeemer type, we need to go into the rest of our code to update it to use it. If we look inside our script instance, for example, we set our redeemer type to be our custom type. We update our wrap. And then when we are making our redeemer to send inside our grab function, we take our value that we sent, this integer, as you call it up here, we cast it to mySillyRedeemer instead of an integer, and then we call Plutus tx.toData. Long story short, if you go back in the lecture video, since all of these objects that we define is of type data, there's some helpful functionality called toData and fromData that converts our object to be something that can be sent across the network to the blockchain. And this is all 6 examples. And so hopefully after all of this, you now have an understanding of how to create your own validator script. So now it's time to go on to the homework. So once again, let's copy our first homework assignment. Go to homework.haskell, copy the whole file, go back to our VirtualBox, our server, and then we copy and paste everything. And so if we read the code, the assignment is inside our validator script. We should validate and release the funds if and only if the two booleans in the redeemer are equal. And so I think if we hit compile, will this actually work? Yes, it does. So if we quickly look at simulate, we can see that give is still the same. However, it's the amount that we're giving. But if we look at grab, there's 2 checkboxes. And so the code wants to return true and release the funds if both of these are the same. So that either means they're both unchecked or they're both checked. When we look inside our validator script, we can see that our datum is of type unit, so we don't care about that. We receive a tuple of 2 booleans, and we have a validator, CTX, or context, and we return a boolean. And so the first thing we need to do is we need to define our variables that we're using inside our validator script. And so our datum is just the unit type. And the tricky part here is how do we refer to our booleans? And the answer to that is we just have parentheses, and we use AB. A represents the first Boolean, and B represents the second Boolean. And then we'll just keep the third variable to be underscore because we never use it. Now, for the actual code, we want to unlock this if they are equivalent. So the quick and easy way is just saying if A equals B. And this will return true if they're equivalent, i.e. if they're both true or they're both false. Next, we need to implement the types that we're expecting. And spoiler alert, the rest of this code essentially is just copy and paste from example 5 or 6. And so I'll just quickly go at it. So the first thing we need to do is we need to find the type, specifically our datum in our redeemer. Great. So now that we have our type, we need to create our script instance, and this is with Template Haskell. Right, so we define our script instance. Now we need to use our script instance and create a validator object. With our validator script, we need to generate the hash, which then will later be used in our source address to get the address of our script. And that's it for this assignment. So let's compile and see if the code works. All right, compile successfully. Let's go simulate. So while one is giving, let's say we lock up 5 eta. Let's just wait one block. And then while 2 wants to grab the eta, and we'll just keep this the same. And we'll also wait 1. So we hit evaluate. What should happen is that while 1 will lock up 5 etas. So they'll have 5 left because they both have a total of 10. And then while 2, because both instances are false, we'll redeem the eta and get 15. And we scroll down, we see that is exactly what happened. While 1 locked up 5 eta, so now they have 5. While 2 redeemed it, and so they have 15. Now, if we go back to our example, and let's say we make one of these true, we hit evaluate, what will happen is that while 2 will not be able to unlock the eta. And we scroll down, and we see that's exactly what happened. While 1 still locked up their 5 eta, but while 2 was not able to retrieve it, so they still have 10. Now, I won't go through the other permutations, but I can show you that they work. And so that's how you would implement homework 1. All right, so for the final assignment, we have homework 2. Let's copy and paste. Go back to our VirtualBox and paste. This time, our assignment is we're doing the exact same thing. Our validator script should validate only if the 2 booleans in our redeemer are equal. And the only difference this time is that we have a redeemer object, and instead of making it an integer, we're using something called a record, which is a fancy way of saying we are creating an object that takes in 2 booleans. Let's implement our validator script. The first variable, our datum, is still a unit. The interesting part now is how do we get the variables, the booleans, from our redeemer? And so to do that, you just need to define the variable, or the type, my redeemer. To get the booleans inside of it, you just reference them. And so we want to unlock the funds only if A and B are equal. So it's the same exact thing, except instead of using a tuple, this time we're using a custom data type. And so we just do A equals B, and that should be it. The rest of this code is exactly the same. So much the same that I'll just copy the code we've written from our previous example. Paste it over here. And the only difference now is we need to change the types. So instead of a tuple boolean, we just set my redeemer to be the redeemer type. And the rest should be exactly the same. So let's compile our code. Well, this is what you get for copy and pasting. I know why. It's because we didn't copy and paste the type object instance. All right, so we paste this into. And so instead of using that tuple, again, we just use my redeemer. And now we compile, and now it should work. So let's hit simulate, and the same example. While 1 gives lock out 5 eta, we wait 1 action. While 2 grabs, keep this the same for now, and we wait another 1. And what should happen is wallet 2 should redeem that 5 ADA, giving it a total of 15 ADA. Now we scroll down and we see that indeed, yes, that's exactly what happened. Wallet 2 now has 15, wallet 1 has 5. Now let's go back to one more example. We set flag 2 to be true and we evaluate again. You scroll down and let's see, wallet 1 is 5, wallet 2 is 10, and that's exactly what happened. And so that's how we would implement this. Now, I probably should have mentioned this earlier, but the solution to homework 1 and homework 2 will be in my GitHub repo, which I will include in the description below. That's a wrap for the second week of the Plutus Pioneer program. Hopefully at this point you understand what a validator script and how it plays in the Cardano blockchain, and then how to create your own, going from the very basic function definition all the way to setting up errors, sending in custom redeemer types, and then eventually actually creating your own custom redeemer for the validation script. I personally found that the best way to learn is actually just typing the code yourself while you follow along. So if you haven't done that, I highly recommend just going through the videos again and then follow along that way. However, you do what's best for you. And so that's the end of the lecture 2, and lecture 3 will